Okay, so to conclude today's session, we have Tibor, who is going to tell us about topological quantum spin-glass order and quantum LDPC codes.
Right, thank you very much. And I will talk about these two papers plus some related upcoming work from the end of last year, which were done together with this set of people. In particular, Benedict was kind of very instrumental in a lot of this, what I will talk about. And my talk will be, I think, kind of nicely complementing Alvaro's talk from this morning, in that I will also be thinking about Gibbs states and then preparing Gibbs states, doing some local dynamics. But I'll be interested in sort of the opposite limit, in the sense of I'll be interested in finite order one, but low temperatures, where you can have some non-trivial structure in your Gibbs states, and how that non-trivial structure influences your ability to prepare those states. So just to start off, let me think about classical Gibbs states for a moment. So I have some classical system of n spins. I have some distribution, probability distribution over the 2 to the n spin configurations, which is of the form e to the minus beta h, where h is some Hamiltonian or some energy function. And of course, I can always write any probability distribution in this form. So to make this more meaningful, I have to impose some locality conditions on this energy. And there's kind of a hierarchy of conditions you could impose, where the most local, and in some sense the most physical one, is to imagine that your spins live on some finite dimensional lattice, and you only have kind of spatially local or geometrically local interactions between them. This is like the usual setup of something like a 2D Ising model. But you could generalize this to think about some less restrictive notion of locality, where your spins live on some graph, which doesn't necessarily have to fit in any finite dimensions. It could be something like a hyperbolic lattice or some complicated random graph, but still in such a way that everyone has finitely many neighbors. And I don't know if this has a good name, this notion of locality. I'll call it the graph local. And finally, you could go to the limit, which the first talk in today's morning session was about, which is when you allow arbitrary k local interactions. So still only kind of each term involves finitely many spins, something like two-body interactions, but in principle all-to-all. And there's got lots of good reasons to care about this kind of Gibbs state. So there's obviously a physics reason, especially in this first case, which is that they describe thermal equilibrium of many-body systems. But there's also kind of good reasons to care about the more general cases. So just in terms of probability theory, these kind of graph local things describe various probability distributions that you have. If your degrees of freedom, your random variables, have some notion of kind of neighborness or only sort of local interactions or local correlations between things, which actually occurs in like a large number of interesting cases. And for example, things like machine learning, you have things like this, or maybe even versions of this k-local case. So the question is, what kind of structures can you have in these Gibbs states? What kind of qualitatively different things can occur? And especially, we are interested in cases where the structure is robust in some sense, that if I change the Hamiltonian or the temperature a little bit, the structure is still there. So the simplest example of some non-trivial structure is just the 2D Ising model. So I have spins interacting on a square lattice. And what I see is that there's a phase transition between high temperatures, where it's sort of some trivial looking distribution, to low temperatures, where what I see is that the distribution sort of fragments into two components, that there's large weight on some positive magnetization and large weight on negative magnetization, and then low weight in between. So there's some sort of fragmentation. That's like a basic example of the kind of non-trivial structure that you can end up with. So you have two components which are different macroscopically, and they are related to each other by symmetry. So it's an example of symmetry breaking. But it is also a kind of dynamical way of thinking about it, which is that if I was trying to run some local Monte Carlo dynamics to try to sample or prepare this state, what I would see is that if I start near one of these components, I get stuck there for a very long time. Sometimes it's exponential in system size. So that means that the system acts as a kind of passive memory that remembers one bit of information. And this is how something like a magnetic hard drive works. So this is an example of some non-trivial structure, but what are some more exotic examples? And once we go beyond geometric locality to these sort of more non-local examples of k-local or graph-local Hamiltonians, we can get kind of more exotic versions of this, which goes by the name of spin glass order. So the standard model of this is the Sherrington-Kirkpatrick model, which is still an Ising model, but with all-to-all interactions and with sort of random couplings that can be positive or negative. And what you end up with is some complicated energy landscape with lots of local minima. And what happens is that at low enough temperature, your Gibbs state fragments into not just two components, but a very large number of components. The number of components actually grows with system size. And these components are not related to each other by symmetry, and many of them correspond to these local minima. So they kind of only contain high energy states. And again, you can think of this as the system having a very large memory in this case, that you can start in lots of different initial states and remember where you started for a long time, which is related to things like the sort of idea of an associative memory in something called the Hopfield model, which is a version of this. And this kind of spin glass structure, this fragmentation into many components, actually appears in lots of different models. Once you go beyond geometric locality, there are lots of kind of computational problems, things like random satisfiability, and so on, where you have some structure like this, that you have a distribution that sort of fragments into more and more components as you tune some parameter like temperature. So this is something that can happen. Now, what happens if we go from classical to quantum, if you think about quantum Gibbs states? So again, something that looks like E to the minus beta h, but h is now a Hamiltonian operator, which can have non-commuting terms or generally not be diagonal in some classical basis. So what are the new phenomena that can happen? And here, the simplest example of something non-trivial is something like the four-dimensional toric code. So in order for this to happen, to get something non-trivial at finite temperatures, you have to go to sort of 4 dimensions. The 2D toric code is only non-trivial at 0 temperature. But in this 4D version of the model, you get topological order at finite temperatures, which manifests first in the fact that you have some long-range entanglement, which I will define in a few slides. And you have a passive memory, which in this case can preserve a quantum bit of information rather than just classical bits. So that's kind of one new thing that you can get, which you cannot get in the classical examples. So you have these two sort of different kind of structure that can appear. One is this classical spin glassiness, where you have many components, including these sort of high energy ones that are not related to the actual ground states. The other one is topological order, manifesting in long-range entanglement and quantum memory. And my talk will be about answering a simple question. Why not both? Can you have both of these in the same model at the same time? So you can think of this as the following in some kind of very coarse-grained picture of phases, where you can generalize this like simple symmetry breaking picture in two directions, either in the directions of glassiness or in the direction of topological order. And what I'll talk about is kind of completing this square where you have both happening at the same time. And I will refer to this as topological quantum spin glass order. So the rest of my talk will have two parts. So first, I will just try to make this sort of sketchy definition and idea more precise, what I mean by these different kinds of structures and having them together. And in order to do so, I will also have to think about the issue of sampling from these Gibbs states, the dynamics that actually takes you there. So that will connect to Navarro's talk. And in the second part, I will show how this sort of topological glassiness is realized in some particular family of models. Okay, so that this definition isn't empty. There are actually systems that satisfy it. So my goal now is to think about Gibbs states of local quantum Hamiltonians, where local, again, can be one of these different classes of k-local or graph-local or geometric local. And I want to define in full generality what we mean by this Gibbs state having kind of multiple components. So in the Ising model, we could just measure it in terms of magnetization, that there are two components with different magnetizations. But in a more general case, you might not have such a simple classical label. So you want to have some notion of what it means for the Gibbs state to sort of fragment into these multiple components. And what's a good definition of that? So as I mentioned, the reason in the classical case, this fragmentation is a useful definition, or one reason why it's useful, is that it tells you something about dynamics. If you try to sort of run Monte Carlo to sample from your classical distribution, this fragmentation tells you that it's hard to do that in some sense, that you can get stuck near one of these components for a long time. So we would like to have something similar. We would want to have some notion of these components that ensures that if I try to prepare the state using local dynamics, I'll get stuck there in each component for a long time. So in the classical case, this result that relates the structure of the state to the dynamics is called the bottleneck theorem. So what we're aiming for is some quantum version of this bottleneck theorem, which applies for this kind of quasi-local Gibbs samplers that you heard about this morning, that prepare the Gibbs state using some local update rules or quasi-local update rules. So the question is, when do these experience some sort of bottleneck, when they get stuck in certain initial states? And so the statement that we proved is the following. I'll make it more precise in a moment, but just in some very coarse-grained version. The idea is that we have some quantum channel which prepares the Gibbs state in question. The steady state of this is the Gibbs state. So in Alvaro's talk, he talked about Lindbladians. I will talk about quantum channels, which are kind of the discrete time version. But you can, if you want, you can think of this channel as just evolving with some Lindbladian for some small amount of time, if you want to think about Lindbladians instead. And what we show is a sufficient condition for a quasi-local quantum channel to get stuck in certain initial conditions. So the initial condition that we care about, they have this form that we take the actual Gibbs state and we project it down to some subspace of the Hilbert space. And what we show is that if this subspace satisfies certain conditions, then this projected version of the Gibbs state is also approximately a steady state. In particular, if I take this initial state, evolve it for one time step, and ask how much does it change, what is the time derivative, we can upper bound this time derivative by some quantity that depends only on the properties of the Gibbs state itself. And then in the cases of interest, this upper bound will go to 0 in the thermodynamic limit. Okay, and if this happens, then we have some component that's really in the thermodynamic limit, sort of survives for infinitely long times. So how do we do this? So let's see how this works in the classical case first. So in the classical case, you can kind of illustrate how this bottleneck theorem works by just thinking about a classical random walk. So imagine some classical particle performing a random walk on some graph. And here I drew a graph which has some sort of bottleneck in the sense that there are these two big regions, but there is this narrow region in between that you have to get through to go from one side to another. And the question is, how long does it take? If I start on one side, how long does it take before I end up kind of sampling the whole space? And what the bottleneck theorem tells you, or one version of this bottleneck theorem, is that the mixing time, which is the time it takes to sort of cover the whole space, is lower bounded by this ratio, which is the probability of this big subspace A relative to the probability of this sort of narrow intersection that you have to get through. So the narrower the intersection, the longer this takes, the longer you get stuck on one side or the other. And you can generalize this from a random walk to some more general case where you could imagine that it's not just sort of the number of connections, but each of those is weighted by some matrix element of your Markov generator that tells you how likely you are to go through. But it's still the same general idea. And for example, in the Ising model, your two big regions would be these large positive or negative magnetization regions, and your bottleneck would be this empty region in between where you have low magnetization. Yeah.
So region in the state space or
state space. So this is like configuration space. So this is like the 2 to the n dimensional space.
Like how do you determine like what states are really like?
I'll get to that in a bit. Here, you should think of it as something like Hamming distance, that you have to flip many spins to get from here to here. Okay, so here is the sort of quantum version that we proved. So you have some channel with some steady state rho, and it's useful to think of this channel in terms of its Krauss representation, some Krauss operators, Ki. And what we want to do is split the Hilbert space. So now instead of configuration space, we have to think about Hilbert space. And we'll split it into 4 orthogonal subspaces, A, B1, B2, and C, where this B1 and B2 together will be our bottleneck. Some technical reasons in the proof why we have to sort of split it into 2 smaller regions, but you just think of the 2 together as this kind of narrow bottleneck, and then A and C are on the 2 sides. And what we assume is that all the Krauss operators only have non-zero matrix elements between kind of the neighboring regions in this decomposition. So if I think about some trajectory of pure states, if I start in A, I have to go through first B1, then B2, and then C in that order. I cannot jump through any of them. That's the assumption that we make. And then what we show is that if this is true, then this time derivative, how much does it change? How much does the state projected down to subspace A change in one time step is upper bounded by a ratio, which is only related to the probabilities of B and the probability of A. So this is kind of similar to this classical bottleneck result that I showed you on the previous slide, but it's different in one sense, and that difference actually has to do with the fact that this is quantum and not classical, which is the appearance of the square root in this bound. So previously it was just a ratio of probabilities. Now one of the probabilities shows up under a square root. And this has to do with the fact that when you actually go through this bound, you have to worry about kind of off-diagonal matrix elements, that your Gibbs state can have some off-diagonal matrix elements between these different subspaces, which is sort of specific to the quantum problem. So even though the result looks pretty similar to a classical case, there's actually some physical difference why it's not exactly the same result. Okay, and so this is an upper bound on the time derivative of how much you change in one time step, but then you can kind of iterate this to get a bound on the mixing time, which is the time it takes to actually reach the steady state, to reach the Gibbs state, starting from this initial state, which is now sort of lower bounded by basically the inverse of this ratio. So if this ratio is very small, then it takes a very long time to relax. So this was kind of a general version for any quantum channel, assuming this condition that you can find this decomposition into A, B, and C such that your Krauss operators kind of only connect the nearest neighbors. But now we can apply this to kind of a many-body system using locality. So if I assume that I have some system of n qubits, I will define the bottleneck ratio kind of by locality, and this is also which is the following. So let me take some subspace of the many-body Hilbert space V. I can define a neighborhood around this subspace as all the states I can get to by some local operations. I take a state in the subspace, I apply a local operator, where local is at most R local, and look at all the states I can get to that define some larger subspace. And now I can take the complement of the original within this larger subspace, and I will call that the boundary, the states I can get to by local moves that are not in the original. And this boundary will play the role of B. This will play the role of this bottleneck region. That it's something that I have to go through. If my dynamics is local, if my Krauss operators are local, I cannot escape this subspace V without going through this boundary region. So if the ratio of probabilities of boundary and the inside is sufficiently small, then for any local dynamics, I will be stuck inside time. And as stated, this assumes that your Krauss operators are strictly local. They are only, let's say, R local or R half local. But if you think about the more general case of sort of quasi-local dynamics, then you just pick up some extra errors which are exponentially small in the width of this region in R, and then we will be interested in the case where we take R to infinity at the end. So these errors will also go to zero exponentially. Yeah.
Is there any like explicit example where you definitely need this for?
I guess not. Yeah, I don't know any. So in many examples, you can get away without a square root. For example, if your Hamiltonian is a stabilizer Hamiltonian, yeah, I don't know of any specific example where we need the square root. Well, maybe, but I think that might require extra assumptions. Like I don't know if you could do. Yeah.
I'll fix that.
Okay, thanks. Okay, so this is a general definition for local. If you have some notion of locality, and again, we only really need k locality. We don't need any spatial or geometric locality. So now this gives us a definition of when we say that the Gibbs state has some non-trivial structure, that we say that there is a component of the Gibbs state living in this subspace V if this bottleneck ratio, probability of the boundary relative to the inside with this extra square root, goes to 0 as the system size goes to infinity. And in that case, in the thermodynamic limit, we are stuck in this subspace forever. And then we say that the state is non-trivial if there are multiple such components, at least 2, but the number might be much bigger, for example, in the spin glass examples. And you could kind of do this iteratively, decompose into smaller and smaller parts until you find some extremal thing that you cannot decompose any further. So there is a notion of kind of an extremal component that's like the minimal thing that you can decompose into. And then how many of these are is some measure of kind of how much information the system protects as a kind of passive memory. And physically, the way you should think about these is that these are regions of the Hilbert space which are separated from everything else by some large free energy barrier. So that's why it takes a long time and why it's difficult to sort of escape them. Thank you. And the question is, okay, what kind of different such structures can exist? In particular, this definition applies to sort of both classical and quantum. So how do we distinguish between those? And there are sort of two different ways of trying to do that. One is in terms of the memory properties of the system, whether the system preserves classical information or quantum information. So again, going back to this Ising example, we just had two components, and the only freedom we had is something like how much weight we assign to each of them. So if I start with some generic initial state, which is not near one or the other, but some mixture of both components, then I go to something, then it remains that mixture, and that relative weight between the two components is preserved. So that's kind of one classical bit of information that I'm maintaining. But in a quantum memory, I have a slightly more elaborate structure, which is that in the Ising model, this decomposition was unique. There were two subspaces into which I could decompose, but those were kind of just fixed, set by the magnetization. In a quantum memory, something like the 4D toric code, there's actually different decompositions corresponding to things like the kind of logical Z or X eigenvalues of the encoded information. So those give you two different ways of decomposing your state into two subspaces. And in the more general case, kind of a generic steady state that's preserved has some structure like this, where it's some arbitrary 2x2 density matrix that describes the encoded logical information tensored with some junk that's just kind of fixed. That's the same for all steady states. So that's one distinction that you can make between classical and quantum in terms of the structure of this subspace, this space of all the different Gibbs state components. But there's another way you could try to distinguish them, which is in terms of the entanglement structure. So another distinction between classical and quantum that applies, for example, to the 4D toric code is that you have some long-range entanglement in the 4D toric code, which for mixed states we can define as follows. So for a pure state, we say that the state is short-range entangled if you can prepare it in a finite amount of time or in a finite depth circuit, where maybe you can relax this from finite to logarithmic or polylogarithmic. And then for a mixed state, you say that it's short-range entangled if it's a entangled pure states, and it's long-range entangled if it's not a mixture of short-range entangled pure states. So another question you can ask is whether the Gibbs state as a whole or one particular component of the Gibbs state is long-range entangled or not. And one question here, which is sort of not close related to my main topic, but sort of interesting, so I want to mention, is that in things in, for example, the 4D toric code, you have both of these properties appearing at the same time. You both have a quantum memory and you have long-range entanglement. And those are in some ways related, but you could ask, is that necessary? Do you only ever get those two at the same time? So it's actually interesting that we have an example that's a kind of a counterexample to that in finite three-dimension geometrically local interactions and so on, where you have long-range entanglement in this sense, but there is no quantum memory. So it's kind of an interesting sort of counterexample to the idea that maybe these two things kind of necessarily go together. Yeah.
So, to the fermion weird speaker, is it also similar example?
It's a similar example, but it's a finite temperature state here. So that's not a finite temperature state of something. This is kind of a similar example, but you have to go to like one dimension. Yeah, here there is a finite temperature, but you have to go to 3 dimensions instead of 2 to get that. Yeah.
Regarding should I think of the model that more is of the energetics or like the exciting distance? Like there are different, for example, if it's a free energy barrier, I can have a scenario where the energy barrier is tall, but it's actually very narrow, so that quantum mechanics is no problem. But thermal, it's so in this case, like quantum mechanics,
well, so in the version that we have, you kind of need both in the sense that you want the width of the bottleneck to sort of diverge with system size in some way. At least, so if you fix the width of the bottleneck, it gives you a bound on how quickly you mix for like sufficiently local dynamics. But if your dynamics is sufficiently non-local, you can jump over, then this bound doesn't imply anything. So that's why you kind of want to take the width to infinity in some way, so that for any local dynamics, you get something non-trivial. But of course, you don't want the width to go to, if you take the width to be too large, then this ratio might end up not being small. So there is some trade-off between them. But in the interesting examples, you can kind of do both. You can take the width to infinity, but you take it slowly enough such that the ratio still goes to 0. And that's kind of what you want. Well, I don't know if a finite temperature Fermi liquid necessarily has long-range entanglement by this definition, but okay. Also, I should say that this is like kind of a gapped or short-range correlated or what have you version of this. That yeah, like if you allow things that are sort of have power law correlations and things like that, then maybe this is not so surprising. But the fact that you can have it via like sort of correlation like this finite is maybe more interesting.
It's wrong, but if someone intuit that if it's long-range entanglement, it must have a quantum memory. Like what would be the rationale? I mean, I'm asking this because I feel like long-range entanglement and quantum memory is something independent, but if someone believe it, which is wrong, what would be the rationale?
I see.
Since you presented it this way.
Right. Well, I mean, I think it's more just like, I think, at least in the example, all the examples I knew of before these things sort of coexist in something like the 4D toric code. Again, like not counting kind of sort of long-range correlated examples. I mean, and there is sort of maybe a relationship in one direction that will probably need some sort of long-range entanglement to have a quantum memory. But I guess, yeah, this shows that the converse is not true, which maybe it's not surprising. It was a bit surprising to me, but maybe that's just me. But at least it's the first example that I know of under some assumptions. Okay, so these are sort of two ways of saying when your state is quantum. So putting all of this together, we have a Gibbs state, we have a notion of decomposing that Gibbs state into these components, and then we can ask several questions about that decomposition. One is, can we use it to store quantum information? Another is, are the components long-range entangled? But we can also ask these questions having to do with spin glass behavior that I mentioned at the beginning. So we can ask how many components there are. Does it grow with system size? Does it even grow maybe exponentially? And also, are there these components that don't contain any ground states, that kind of only made up by high energy states? And so the claim that we make is that there are some models where the answer to all of these questions is yes, that you have kind of a coexistence of all of these features, and this is what we call the topological quantum spin glass. And the examples we have of these are based on certain quantum error correcting codes. So that's why we talk about next, is explaining what these codes are and then why they have these properties. Just stopping for a second to see if there are any more questions. Okay, so if not, then I'll change gears slightly and introduce these error correcting codes and then say why they have these sort of combination of properties. And the general sort of roadmap for how the argument works is that I will start with the classical versions of these codes, classical codes. And I will argue that these classical codes satisfy these definitions of a classical spin glass, that they have this sort of complicated landscape with many local minima that are stable at low enough temperatures. And then I will use some ideas from the theory of error correcting codes allow you to turn classical codes into quantum error correcting codes, that you can take classical codes, combine them in a way and get a quantum error correcting code. And by doing it this way, what we end up with will inherit properties of the classical code. It will inherit this kind of energy landscape, but by virtue of being a quantum code, it will also have these various quantum features, such as long-range entanglement. So what is a classical code? So we have some system of n classical spins with 2 to the n configurations. And we want to pick out of these 2 to the n configurations some subset which will be our code verbs that we are using to encode classical information. And we do it by imposing certain constraints called parity checks, which is that some subset of the spins should have a total parity that's +1. So in kind of foreshadowing some quantum language, I can write this check as some product of Pauli Z matrices. And then we want this product to have eigenvalue +1. So I put those all together into a Hamiltonian with an overall minus sign. And then the ground states of this Hamiltonian will be these code states. And we'll impose a locality condition, which is kind of this intermediate kind of locality that I introduced at the beginning, which is that all of these terms involve a finite number of spins. Also, conversely, every spin is only involved in a finite number of interactions. And this condition is called as a low density parity check, or LDPC code. And one kind of particular way of realizing this is something like the following. Imagine taking some graph and then placing your classical spins on the edges of this graph. And then if I look at any vertex of the graph, there is some finite number of spins surrounding it, and I can define interaction terms on those local bits nearby. So that sort of, by definition, is going to satisfy this condition. This is called a tenor code. And these codes are usually described by the set of 3 numbers, n, which is just the number of physical degrees of freedom, k, which measures how much information I encode or how many ground states I have. In particular, number of ground states is 2 to the k. And d, which is the code distance, which is how far in Hamming distance are the different ground states from each other, how many spins I need to flip. And people are particularly interested in the extreme case where k and d both scale proportional to n. These are called good codes. So you have a finite code rate that the amount of encoded information scales linearly with the amount of physical bits that you have to use. And you also have a very large code distance. You have to flip lots of spins to get to a new code word. And that's important for making it robust against noise, because your noise is randomly flipping spins. So the further your code states are, the sort of more protected they are against noise. And getting these good codes really requires you to go beyond spatial locality in finite dimensions and think about these more complicated graphs. In particular, you need something called an expander graph, which is roughly speaking a graph where boundary is proportional to volume. Or another way of saying it is if you take some ball of radius r on the graph, the volume of the ball grows exponentially with the radius, which is not something you can get in finite dimensions. And from our perspective of arguing for this sort of glassy behavior, the property that these codes have is something that I will call linear confinement, which is physically is the statement that if you imagine starting in one of the ground states and you imagine flipping spins kind of one by one and asking what is the energy cost, how does the energy go up as a function of the number of spins you flipped, this growth is linear, that sort of that's why I call it linear confinement. Mathematically, there is kind of a nice way of writing it that you can represent your spin configurations as kind of classical binary vectors of zeros and ones, where you put a 1 if a spin is down and a 0 if the spin is up. And then the energy is kind of a linear function of it. There is some matrix, binary matrix, that you can apply to your vector, which turns it into a different binary vector that tells you which of the terms in the Hamiltonian are unhappy. So in a ground state, you just get 0, they're all happy. In an excited state, you get some zeros and ones, where the 1 tells you which of the terms have been excited in this particular spin configuration. And the energy is just the length of this vector, the number of ones in it. So this linear confinement means that if the length of your vector, so the number of spins you flipped, is sufficiently small, smaller than some fraction of all the spins, then the energy is lower bounded by something that's proportional to the number of things you flipped. Okay? So intuitively, the picture is something like the following, that I flip a spin, I create some excitations, and then I try to get rid of the excitations by flipping more spins, but they sort of proliferate, they spread out on this expander graph, and I kind of have to cover the whole thing, or some fraction of the whole thing, before I can start annihilating the excitations. And this is very different from what you get in finite dimensions, where the energy cost is always limited by the size of the boundary. If I have something like a domain wall, so it's always growing kind of slower than linearly. And an immediate consequence of this linear growth of the energy is that I can define these Gibbs state components around each of the ground states at low enough temperatures. Because if I define my subspace as things within some like Hamming distance of the ground state, and then my boundary will be things at a slightly further away Hamming distance, then the boundary will only contain states which have a proportional to system size higher energy than the ground state. So they have some exponentially small probability in the Gibbs state. And now, even if there's exponentially many of them, this exponentially small energy factor will always dominate at low enough temperatures. So the ratio will always go to 0 exponentially. So if I start near a code word, my Monte Carlo dynamics will be trapped near that code word for exponentially long time in system size. So these are components that are kind of close to the ground states. But what I really want for a spin glass is to also have some other components that have nothing to do with the ground states, but are instead kind of local minima of the energy. And we can argue that those also need to exist. And the way to do that is the following, that because the energy is sort of linear in this representation of the spin configuration, you can use a triangle inequality, combine it with this confinement condition. And if you do that, you get the following, that if I take any two configurations which are close to each other in Hamming distance, their energy difference is lower bounded by something that's proportional to their Hamming distance minus something that's proportional to the energy of one of them. And the upshot of this is that if the energy of of this reference state is low enough, it's low below some particular energy density of the whole system, then as I try to flip spins and get far away, there will be some intermediate point where the energy goes up by something that's proportional to system size. So I have some situation like this where maybe initially the energy doesn't go up, but at some point I need to go through a barrier that's proportional to system size. And then by the same argument as before, that means that at low enough temperatures, this will take exponentially long times, that I will be trapped near this local minimum. And this is true for any state at low enough energy densities. And then you can do a kind of counting argument that shows that not all of those can be close to a ground state. There must be many more of these components than the number of ground states, in fact, exponentially more. So the actual landscape looks something like this. So you have ground states, but you have a bunch of local minima, which are all stable at low enough temperatures. Well, I mean, what's certainly true is that in order to, like, here are two configurations, which are sort of maybe at similar energies, but they are globally very different. There's some global rearrangement that you have to do. And if you were trying to do it step by step, you would have to go through some barrier of high energy or higher than either of them. I don't know if that answers your question. Okay, so you have this sort of glassy landscape with lots of local minima. So this completes kind of the first part of the argument that in the classical codes, you indeed have this sort of classical spin glass features of many minima.
Question.
Yeah.
Maybe it's unrelated, but is it possible to have a classical spin glass with extensive exact degeneracy?
So well, it depends on what you mean by exact degeneracy, but in some sense you have that here. So you have the number of exact ground states is also exponential. So if that,
On top of that, you have a near energy.
But on top of that, you have exponentially more other things which are not ground states, which are still stable at low enough temperatures.
So if you have a high dimensional random bond Eisenhower classical,
Mm-hmm.
does it have a
So
extensive degeneracy?
So for example, in the Sherrington-Kirkpatrick model, which is like all-to-all interaction with random signs or random couplings, you don't quite have that. First of all, or you only have two exact ground states. You don't have more than, because here the large number of ground states comes from the fact that there's actually like a large symmetry group. You do have a large number of these local minima, but not extensive, I think, in the Sherrington-Kirkpatrick. It's exponential in system size to some power, I think.
So for, I guess, most of the spin model with random bonds, you get non-extensive ground state degeneracy. Yes.
Yeah, so well, certainly in finite dimensions, I don't think we can get it to be extensive. Right.
A's are not random. A's are all non-random.
Yeah, so in the models I'm looking at, there is no random. Maybe I should emphasize that there is no randomness anywhere in the models I'm looking at. That's why they actually have a large symmetry group. That's why they have exact degeneracies. When you have randomness, exact degeneracies, you tend not to get, maybe other than some twofold from some remaining Z2 symmetry. But you can still have lots of these sort of quasi-steady states. Okay, so now we want to go quantum. So just a very brief introduction into the quantum version of error correcting codes. So the idea is that we have some Hamiltonian, which now has two types of terms. One looks like a product of Pauli Z matrices. The other one looks like a product of Pauli X matrices, but they still commute with each other. So this is a fully commuting model, kind of like the toric code. And the reason you need these two is because in a quantum code, you have to protect against more kinds of errors. You have spin flip errors, but you also have phase flip errors. And to protect against both, you sort of need two different kinds of terms. And again, you can define these parameters. K is the ground state degeneracy, or 2 to the K is the ground state degeneracy. And there's a code distance, where again, now there's two types. You can imagine applying some product of Pauli Z's or Pauli X's to connect ground states. So there's two types of distances, an X and a Z distance, and the minimum of the two is the actual code distance. And unlike the classical case, where these good codes, where K and D are proportional to N, have been known for a long time, in the quantum case, it's a relatively recent result from the last few years that you can actually get these. And the reason it's complicated to get these is that it's not enough to have some sort of graph. You kind of need a higher dimensional version of a graph while still having this sort of expansion property, because you need some notion of a plaquette. Basically, you can, similar to a toric code, you can think of these two terms as living on vertices and plaquettes of this complicated object. So you need to build something complicated that's more complicated than just a graph. And one way of building something like that is by starting with a classical code and kind of going from there, combining classical codes to get one of these quantum codes. So this is what I will explain. And there are different versions of this. This is kind of the simplest version called a hypergraph product construction, where in some sort of coarse grain level, it's some black box which takes two classical codes and it spits out a quantum code. So it's a way of building a quantum code from two classical codes. And it's best illustrated in the simplest example, where these input codes will be just one-dimensional classical Ising models or repetition codes, and the output is going to be a 2D toric code. But the idea is that the construction works for any inputs. So I could exchange the inputs for one of these complicated classical LDPC codes and then get the output. And in a slightly physicsy way, the way to explain what this construction does is you first take two Ising models and construct a 2D Ising model from two one-dimensional Ising models and turn them into a two-dimensional Ising model. And you can think of this as something like a coupled wire construction, that I take copies of my one-dimensional Ising chain, and then I use terms from the second Ising chain to couple these to get a 2D model. And then there is kind of a well-known duality that you can apply to a 2D Ising model, turn it into the toric code. This goes by the name of gauging. And the point is that both of these steps you can generalize to arbitrary classical inputs. You can take arbitrary classical codes, do this kind of coupled layer construction to get a different classical code, and then you can apply this kind of duality transformation to get a quantum code out of it. And in general, what happens is that the number of degrees of freedom multiply together, but the code distance is kind of only the minimal of the distances of the two inputs. Like in the toric code, your logical operators that connect different ground states, they only have to wrap through the torus in one direction or the other, but not both. So they only go with square root of the number of degrees of freedom. And if I apply this to one of these sort of classical LDPC codes, I end up with these sort of higher dimensional versions that correspond to a quantum LDPC code. Okay, so this is the next step in the construction. You take these classical things, take a product to get a quantum code. And now our claim is that the thing you end up with if you do this, if your classical code had these properties that we wanted, will be one of these topological quantum glasses. So now I'll spend the remaining 5 to 10 minutes to just explain how that comes about. So first of all, what I need to argue is that this quantum code I get still has the same sort of energy structure, that it still has these local minima that host kind of stable Gibbs state components at low enough temperatures. And this comes from the classical inputs, except there is sort of one twist that you have to take care of, which is that you still have this kind of linear growth of the energy. If I start in some reference state and I apply some set of Pauli operators to it, the energy grows up kind of linearly in the number of qubits I'm acting on. But it only keeps growing up to some threshold, which is square root of the number of qubits, not linear as it was in the classical case. This kind of comes from this hypergraph product construction. And what that means is that you have to slightly modify your definition of these components. Because previously in the classical case, I could just define a component as like all the states within some Hamming distance of my reference state. But now I can't do that because if I do that, if I take that radius to be proportional to system size, I get too many things. I get kind of outside of this local minimum. So instead, what you do is rather than just kind of count the number of flips, you want to think of something like number of connected flips, meaning that I can write a state as some reference state and then some errors on top of that state. But rather than just saying that the total size of the error should be small, I want to think of how those errors are distributed now in real space. And I want to say that the sort of largest connected component is small. So this is kind of like, if I think about something like a 2D-izing model at low temperatures, there's a finite fraction of spins pointing in the wrong direction, but they kind of dilute. They form lots of small islands. They don't form like one giant island. This is a generalization of that idea. So this will still be true at low enough temperatures. And so if I define the appropriate subspace this way, then this subspace will still host a stable component. This kind of bottleneck ratio will be small, not exponentially in n, but exponentially in square root of n, but it's still good enough. And the same sort of counting argument as before tells you that there are a lot more of these components than the number of ground states. So most of them actually have to be this kind of high energy states, these local minima, not the actual global ground states. So you still have this sort of glassy landscape, but I also want to have some quantum properties. So there are two things I promised you. One is that there is some sort of quantum memory. So what you find is that there's actually a kind of interesting structure. You have some mixture between a quantum and a classical memory in these systems, in the sense that you have some exact symmetries of the Hamiltonian. There are some logical operators that exactly commute with the Hamiltonian, that are the things that take you between the different ground states. So because there are these exact symmetries, if you look at your energy landscape, you actually have kind of k copies of the same landscape, each containing a single ground state, but lots of local minima. And there are two different ways you could try to encode information in it. You could encode information sort of between these different copies, or between the different minima within the same copy. And between the different copies, you can encode quantum information because those states are kind of locally indistinguishable. So that information will be actually robust against any noise. Within the same copy, but between different minima, you can only encode classical information because those have different energies, so those are locally distinguishable. But you can still use it to sort of encode some classical information. So in total, you have some structure like this, where you have two sets of parameters, some classical probabilities that tell you what weight you have in each of the minima, and there is some quantum density matrix that tells you how the information is distributed between the different copies. So it's this kind of this hybrid classical quantum memory that has shown up before in sort of certain context in quantum error correction. So that's one property that you have. And the other thing is the long-range entanglement, where the statement is the following. So the statement is that actually, if you take a typical state at low temperatures, I sample a pure state from the Gibbs distribution at low temperatures with probability 1 in the thermodynamic limit, this is going to be a highly entangled or long-range entangled state that cannot be prepared with a short depth circuit. And the way we argue that is using some recent results from this paper, where the idea is that it can be shown that if I have some quantum error correcting code with a finite code rate and a code distance that is at least logarithmic, then all the states forming this code must be long-range entangled. And then what we can show is that if you take one of these subspaces around one of the local minima and take an arbitrary state from that subspace, and we look at the 2 to the k kind of copies of this subspace, we can pick a state, one from each copy, such that these 2 to the k states together will form a quantum code. And so the k is proportional to n, it's just inherited from the original code that we started from. And the large code distance comes from the fact that the original code had a large code distance and that all of these subspaces are kind of far from each other by the way we constructed it. So this code satisfies the properties of this theorem. Therefore, all of these states have to be long-range entangled. And since the initial state was arbitrary, from any of these local minima, any state, I can construct this code. This means that all of these states must be long-range entangled. So it's actually kind of stronger than what I wanted. It's not only that the Gibbs state itself has some long-range entanglement, but actually all low energy, or almost all, I shouldn't say all, but kind of with probability one, almost all low energy states have long-range entanglement.
NLTS for
Yes, that's why I said I shouldn't say all, because it's like a slightly weaker version of NLTS, where NLTS would say that there are all states with low energy densities are long-range entangled. This says kind of almost all states when
is it for arbitrary temperature?
no, the low enough temperatures. Yeah, for low enough temperatures, if you take a pure state from the Gibbs distribution, then with high probability, it will be long-range entangled. That's the statement. Okay, so that basically brings me to the end. I have one slide which I'm going to jump over and just leave up the conclusions and mention a few open questions very quickly, which is, so we had this bottleneck theorem. It's kind of an interesting perspective on finite temperature quantum systems. It would be interesting to prove that this bottleneck ratio is small in more examples. Think about more examples of this kind of topological glassiness, whether it has any implications at finite dimensions for disordered systems. And also, so the definition I gave is sort of abstract. It would be nice to have some like more measurable order parameters that would diagnose this phase. So these are, I think, interesting open questions. And with that, thank you for your attention.
Thank you for nice talk. And the success of some decoder, for example, like a local decoder like a BP. It seems like according to this energy argument, this seems like a BP must be successful for this type of code. But obviously what we know is that in general, BP solely is insufficient for decoding all the errors. Or even local errors if we usually need idea how does it relate.
Right. So two things. One is that, yeah, so for BP, my understanding is that you sort of want one kind of the system not to have any loops, which is not true in this case. Like in the quantum case, as I showed, you have these plaquettes, so you have some short loops. So I don't know whether that would work, but it is true that there is a local decoder. It's not BP. It's some like more brute force, just kind of minimize the energy decoder would work. Another way of saying that is kind of like is a zero temperature version of like if I run the Gibbs sampler at zero temperature, then it sort of correctly goes back to the ground state.
Okay, thank you.
In the classical case, we have expander graph and it have a classical spin glass order, which due to the geometry, not the randomness. And this quantum model is this a hypergraph product of a two classical expander graph?
Right.
With quantum code, right?
Yeah, that's right. It's not a good quantum code. So it has the code distance is only square root of the number of degrees of freedom, not linear.
Polynomially good quantum or square root good quantum.
Yeah, it's a good enough quantum code. But yeah, so like for our analysis, it's sort of easier to think about this hypergraph product, but you could generalize it to there are versions of this product construction that give you the good codes, which is a slightly more complicated version of a product. And more or less our analysis would generalize. There is sort of one step in it basically where it's not rigorous. So we cannot rigorously say that the good codes also satisfy all these properties, but we are pretty sure that that's true.
One more question is, for the classical expander graph, is the logical operators like trivial? Like, can we just can we figure out what the logical code words are? Then if we know those, like, then for quantum cases, because it's a hypergraph product, the logical operators are also conceivable, right?
So the second part is true. So in the hypergraph product, you inherit the logical operators from the classical code. So once you know the classical logicals, the quantum ones, you know what they look like. But the classical ones are not easy to figure out in general. Like full generality, if I gave you like a classical LDPC code and I asked you to
Yeah, but for generic LDPC codes, yes, but this is not it is just the expanded graph is a very, given rules of how they expand. So I thought it is a little bit easier than just.
I mean, there is some structure that you could try to use, especially like some of these examples have like lots of symmetries, but even there, I don't
I see.
think necessarily finding all the logicals is easy.
Okay, thanks.
Oh, okay. So in classical spin glasses, they're like kind of like classical computational problems where people try to minimize the energy as the best they can. For these quantum spin glasses you've introduced, do you have any sense? I guess I'm wondering, is there any sense in which these quantum ones are harder computationally than the classical ones, either from the perspective of a quantum or classical algorithm?
Not in any way I know how to exactly quantify. Intuitively, I could imagine that something like that is true, like because yeah, you have this highly entangled state, like your local minima are these highly entangled states, which are maybe in some sense harder to find, but yeah, I don't know how to quantify that.
Maybe one more. How, this is also probably hard to answer, but do you have any intuition as to how broadly this topological spin glass order might arise? Like if I just take a random quantum model or a random stabilizer model?
Yeah, so again, I don't know anything for sure. Yeah, well, I guess I have two competing intuitions. One is that given that the classical spin glass is actually sort of in some sense pretty ubiquitous, that like there are lots of problems where you just randomly pick things and you get it. On the other hand, the quantum is harder because you can't just pick things. At least if you want to have like the stabilizer, like commuting stabilizers, then you can just do things completely randomly, which is part of why like the quantum error correcting codes are harder to construct.
I see.
But it's also you don't like stabilizers are easier to analyze. But if I just had like random but non-commuting terms, yeah, I don't know. It's an interesting question.
Thank you.
This is maybe too far beyond the context of the talk, but do you know if I have like maybe a small number of these Gibbs components, and if I tune a parameter and the number changes, do you know if there has to be like a phase transition? You've just been talking about the dynamics, but I'm wondering if you can say anything about the analyticity of the partition function.
Yeah, so one thing I can say, one thing I actually didn't emphasize is that at least in these models, or at least some of these models, this transition from like having a single component to having many does not coincide with any thermodynamic transition, like free energy is sort of analytic throughout. Now these have many components. If you only have two, I think I think I can come up with an example where you just go from like one component to two components in this sense, but there is no like non-analyticity.
Oh, that's awesome.
It's slightly cheating, but okay, I can explain offline.
Please do.
Oh, yeah.
Very quick one, maybe I'll follow up afterwards, but often in spin glass phases, you'll have like a low temperature phase where the spins are frozen, high temperatures disordered phase, but also some intermediate one where it's sensitive to initial conditions and it's like slowly relaxing. Do you know if there exists that intermediate phase here, and what would that correspond to? Okay, wow, I'll let you speak.
This wasn't the setup, but yeah, this is the slide I jumped over, which was my last slide, which is that so all these things I told you about, where we can kind of prove rigorously what happens at like a sufficiently low temperature regime where you have these exponentially many components. Then they're all kind of small, like completely fragmented. But we can also study the problem numerically, like because its stabilizers can kind of do essentially classical Monte Carlo fairly efficiently. And there is actually two transitions with some intermediate regime, where what you have is that you have many components, but it's kind of one that dominates over all of them. So that like there are very special initial states where you would get stuck, but if you pick the random initial state, you would just be in this sort of largest component. And you see that by basically comparing what happens if you cool the system from infinite temperature, where you sort of get stuck at some point and you stop cooling and you're stuck with some finite energy density. So that corresponds to sort of this transition. But if you actually start in the ground state and you heat the system, you stay near the ground state up to some higher temperature before you jump up. So those correspond to these small islands that if I pick the initial condition very specifically as the ground state, then I get stuck there for a higher temperature than the other transition.
Oh, more questions? Okay.
So, is there any observable, if you're given the density matrix, which is maybe fully thermalized, is there any way to detect those two transitions?
Yeah, good question. I probably not. The first one, I would say almost certainly not. If you just given the sort of e to the minus beta h, then that's kind of just dominated by this big sector. And I think you would like any signal coming from the existence of these other things would be like exponentially small. The transition is more interesting. So that's kind of one of the open questions I had of like, can you have some sort of order parameter?
So, anything in your mind or?
Well, I mean, what you might try to do is, so for spin glasses, you have certain order parameters, which are this sort of Edwards-Anderson type things where it's not a naive order parameter. You still somehow want to take into account, like,
right. Which is some overlap of this weird distribution function.
Yeah, or just calculate something in each minimum and then like maybe average the square of that over the minimum or something like that. The question is what should you calculate in each minimum, where probably you want some like it's not some local expectation value, but something more like it's not a Wilson line because it's not quite the toric code, but something analogous to that.
So second transition is from memory to no memory transition, the red transition?
So there's it's first or second, depending on where you start. It's the higher temperature.
Yeah, higher one is a memory transition.
Mm.
I mean, I guess a coherent information was some, not local, but some order parameter in some sense, right?
Mm-hmm.
And so maybe you can just say that coherent information is just the order parameter for that transition.
Yeah, although it's a slightly weird order parameter because it's not just a property of the state itself. It's like some dynamical protocol where you entangle some ancilla initially and things like that. So, but if you're okay with that, then yes, I think that would pick up the first transition.
And yeah, I think maybe we can, let's discuss after.
I think that's enough questions. Let's thank Tibor for a very nice talk.
Thank you.
Okay, so that concludes